last distribution, again, is going to, rather than discrete inputs or a domain that are discrete values, we're going to think about events that could take on continuous values. Something like measuring the height of individuals, right? So the normal distribution, even though it looks intimidating, remember we just talked about what this was. This is standard deviation. This is 2, this is the number pi. You've seen that before, the number e. This x represents our data. The mu is the mean, and this is the standard deviation. So the things that determine this are a mean and standard deviation, and then we have some data that's based on. So same thing, we can just use, instead of defining a function like this, we'll use Python to farm that out for us. So let's call this distribution heights, and that's going to be stats.norm. Right, and then we have the center, or the mean, which is 60, and the scale, which was the standard deviation, which is 2. And again, now that we're working on a continuous domain, what we're going to use is the linspace method, like we used for our functions. And since we know that the mean is 60, let's go 3 standard deviations in each direction. So that would be 6 in each direction. So we'll go from 54 to 66 and put 1,000 points. All right, so here this will be x. And then we can plot it. And again, we want this to be a smooth curve, so we'll use the plot function, and we'll plot x against heights probability density function evaluated at x, and we get the familiar bell curve. Now again, just like we saw with our discrete distribution, the mean of this is the center, and those 2 in each direction, right? That means that this guy is 3 standard deviations, this guy is 3 standard deviations. On average, your data is 2 away from the mean. That's what your standard deviation tells you. Okay. And we can ask the same questions of this distribution. If these are all of the possible outcomes and their probabilities, then the probability of 65 inches is going to be heights PMF 65. Oh, I'm sorry, PDF. And the continuous case, this is a probability density function. All right, and that seems unlikely. And if I look at my plot, that seems to make sense, though. It does, it's way out here in the tail. Probability of less than 50? Well, that's going to be the cumulative density function up until 50 heights. And you see that that's a very small number because our plot ends at 54. 50 would be way out here, and there's almost no area between the curve there. But if we say, what's the height of at least 60? Well, 50%, because half of our data lies to the left of 60. Okay, and that's our normal distribution, kind of the continuous. For us right now, we're going to look at it as the continuous analog of our binomial distribution. And, I mean, we defined it with this. In this case, it's determined by the mean and the standard deviation. So, but we can still look at the mean and the standard deviation.